Semiconductors are crystalline or amorphous solids with distinct electrical characteristics. They are of high resistance, higher than typical resistance materials, but still of much lower resistance than insulators. Their resistance decreases as their temperature increases, which is behavior opposite to that of a metal. Finally, their conducting properties may be altered in useful ways by the deliberate introduction of impurities into the crystal structure, which lowers its resistance but also permits the creation of semiconductor junctions between differently doped regions of the crystal. The behavior of charge carriers at these junctions is the basis of diodes, transistors and all modern electronics. Semiconductor devices can display a range of useful properties such as passing current more easily in one direction than the other, showing variable resistance, and sensitivity to light or heat. Because the electrical properties of a semiconductor material can be modified by controlled addition of impurities, the modern understanding of the properties of a semiconductor relies on quantum physics to explain the movement of electrons and holes in a crystal lattice. Doping greatly increases the number of charge carriers within the crystal. When a doped semiconductor contains mostly free holes it is called p-type, and when it contains mostly free electrons it is known as n-type. The semiconductor materials used in electronic devices are doped under precise conditions to control the concentration and regions of p and n-type dopants. A single semiconductor crystal can have many p and n-type regions. The p-n junctions between these regions are responsible for the useful electronic behavior. Although some pure elements and many compounds display semiconductor properties, silicon, germanium, and compounds of gallium are the most widely used in electronic devices. Elements near the so-called metalloid staircase, where the metalloids are located on the periodic table, are usually used as semiconductors. Some of the properties of semiconductor materials were observed throughout the mid-19th and first decades of the 20th century. The first practical application of semiconductors in electronics was the 1904 development of the cat's whisker detector, a primitive semiconductor diode widely used in early radio receivers. Developments in quantum physics in turn allowed the development of the transistor in 1947 and the integrated circuit in 1958. Properties: variable conductivity. Semiconductors in their natural state are poor conductors because a current requires the flow of electrons, and semiconductors have their valence bands filled. There are several developed techniques that allows semiconducting materials to behave like conducting materials, such as doping or gating. These modifications have two outcomes: n-type and p-type. These refer to the excess or shortage of electrons, respectively. An unbalanced number of electrons would cause a current to flow through the material. Heterojunctions. Heterojunctions occur when two differently doped semiconducting materials are joined together. For example, a configuration could consist of p-doped and n-doped germanium. This results in an exchange of electrons and holes between the differently doped semiconducting materials. The n-doped germanium would have an excess of electrons, and the p-doped germanium would have an excess of holes. The transfer occurs until equilibrium is reached by a process called recombination, which causes the migrating electrons from the n-type to come in contact with the migrating holes from the p-type. A product of this process is charged ions, which result in an electric field. Excited electrons. A difference in electric potential on a semiconducting material would cause it to leave thermal equilibrium and create a non-equilibrium situation. This introduces electrons and holes to the system, which interact via a process called ambipolar diffusion. Whenever thermal equilibrium is disturbed in a semiconducting material, the amount of holes and electrons changes. Such disruptions can occur as a result of a temperature difference or photons, which can enter the system and create electrons and holes. The process that creates and annihilates electrons and holes are called generation and recombination. Light emission in certain semiconductors. Excited electrons can relax by emitting light instead of producing heat. These semiconductors are used in the construction of light-emitting diodes and fluorescent quantum dots. Thermal energy conversion. Semiconductors have large thermoelectric power factors, making them useful in thermoelectric generators, as well as high thermoelectric figures of merit, making them useful in thermoelectric coolers. Materials. A large number of elements and compounds have semiconducting properties, including certain pure elements are found in group 14 of the periodic table. The most commercially important of these elements are silicon and germanium. Silicon and germanium are used here effectively because they have 4 valence electrons in their outermost shell, which gives them the ability to gain or lose electrons equally at the same time. Binary compounds, particularly between elements in groups 13 and 15, such as gallium arsenide, groups 12 and 16, groups 14 and 16, and between different group 14 elements, e.g., silicon carbide. Certain ternary compounds, oxides and alloys. Organic semiconductors, made of organic compounds. Most common semiconducting materials are crystalline solids, but amorphous and liquid semiconductors are also known. These include hydrogenated amorphous silicon and mixtures of arsenic, selenium and tellurium in a variety of proportions. These compounds share with better-known semiconductors the properties of intermediate conductivity and a rapid variation of conductivity with temperature, as well as occasional negative resistance. Such disordered materials lack the rigid crystalline structure of conventional semiconductors such as silicon. They are generally used in thin film structures, which do not require material of higher electronic quality, being relatively insensitive to impurities and radiation damage. Preparation of semiconductor materials. Almost all of today's technology involves the use of semiconductors, with the most important aspect being the integrated circuit. Some examples of devices that contain integrated circuits includes laptops, scanners, cell phones, etc. Semiconductors for ICs are mass-produced. To create an ideal semiconducting material, chemical purity is paramount. Any small imperfection can have a drastic effect on how the semiconducting material behaves due to the scale at which the materials are used. A high degree of crystalline perfection is also required, since faults in crystal structure interfere with the semiconducting properties of the material. Crystalline faults are a major cause of defective semiconductor devices. The larger the crystal, the more difficult it is to achieve the necessary perfection. Current mass production processes use crystal ingots between 100 and 300 mm in diameter, which are grown as cylinders and sliced into wafers. There is a combination of processes that is used to prepare semiconducting materials for ICs. One process is called thermal oxidation, which forms silicon dioxide on the surface of the silicon. This is used as a gate insulator and field oxide. Other processes are called photomasks and photolithography. This process is what creates the patterns on the circuit in the integrated circuit. Ultraviolet light is used along with a photoresist layer to create a chemical change that generates the patterns for the circuit. Etching is the next process that is required. The part of the silicon that was not covered by the photoresist layer from the previous step can now be etched. The main process typically used today is called plasma etching. Plasma etching usually involves an etch gas pumped in a low-pressure chamber to create plasma. A common etch gas is chlorofluorocarbon, or more commonly known freon. A high radio frequency voltage between the cathode and anode is what creates the plasma in the chamber. The silicon wafer is located on the cathode, which causes it to be hit by the positively charged ions that are released from the plasma. The end result is silicon that is etched anisotropically. The last process is called diffusion. This is the process that gives the semiconducting material its desired semiconducting properties. It is also known as doping. The process introduces an impure atom to the system, which creates the p-n junction. In order to get the impure atoms embedded in the silicon wafer, the wafer is first put in a 1100°C chamber. The atoms are injected in and eventually diffuse with the silicon. After the process is completed and the silicon has reached room temperature, the doping process is done and the semiconducting material is ready to be used in an integrated circuit. Physics of semiconductors. Energy bands and electrical conduction. Semiconductors are defined by their unique electric conductive behavior, somewhere between that of a metal and an insulator. The differences between these materials can be understood in terms of the quantum states for electrons, each of which may contain 0 or 1 electron. These states are associated with the electronic band structure of the material. Electrical conductivity arises due to the presence of electrons in states that are delocalized. However, in order to transport electrons, a state must be partially filled, containing an electron only part of the time. If the state is always occupied with an electron, then it is inert, blocking the passage of other electrons via that state. The energies of these quantum states are critical, since a state is partially filled only if its energy is near the Fermi level. High conductivity in a material comes from it having many partially filled states and much state delocalization. Metals are good electrical conductors and have many partially filled states with energies near their Fermi level. Insulators, by contrast, have few partially filled states. Their Fermi levels sit within band gaps with few energy states to occupy. Importantly, an insulator can be made to conduct by increasing its temperature. Heating provides energy to promote some electrons across the band gap, inducing partially filled states in both the band of states beneath the band gap and the band of states above the band gap. An semiconductor has a band gap that is smaller than that of an insulator, and at room temperature significant numbers of electrons can be excited to cross the band gap. A pure semiconductor, however, is not very useful, as it is neither a very good insulator nor a very good conductor. However, one important feature of semiconductors is that their conductivity can be increased and controlled by doping with impurities and gating with electric fields. Doping and gating move either the conduction or valence band much closer to the Fermi level, and greatly increase the number of partially filled states. Some wider band gap semiconductor materials are sometimes referred to as semi-insulators. When undoped, these have electrical conductivity nearer to that of electrical insulators, however they can be doped. Semi-insulators find niche applications in microelectronics, such as substrates for HEMT. An example of a common semi-insulator is gallium arsenide. Some materials, such as titanium dioxide, can even be used as insulating materials for some applications, while being treated as wide-gap semiconductors for other applications. Charge carriers. The partial filling of the states at the bottom of the conduction band can be understood as adding electrons to that band. The electrons do not stay indefinitely, but they can move around for some time. The actual concentration of electrons is typically very dilute, and so it is possible to think of the electrons in the conduction band of a semiconductor as a sort of classical ideal gas, where the electrons fly around freely without being subject to the Pauli exclusion principle. In most semiconductors, the conduction bands have a parabolic dispersion relation, and so these electrons respond to forces much like they would in a vacuum, though with a different effective mass. Because the electrons behave like an ideal gas, one may also think about conduction in very simplistic terms such as the Jurii model, and introduce concepts such as electron mobility. For partial filling at the top of the valence band, it is helpful to introduce the concept of electron hole. Although the electrons in the valence band are always moving around, a completely full valence band is inert, not conducting any current. If an electron is taken out of the valence band, then the trajectory that the electron would normally have taken is now missing its charge. For the purposes of electric current, this combination of the full valence band minus the electron can be converted into a picture of a completely empty band containing a positively charged particle that moves in the same way as the electron. Combined with the negative effective mass of the electrons at the top of the valence band, we arrive at a picture of a positively charged particle that responds to electric and magnetic fields just as a normal positively charged particle would do in vacuum, again with some positive effective mass. This particle is called a hole, and the collection of holes in the valence band can again be understood in simple classical terms. Carrier generation and recombination. When ionizing radiation strikes a semiconductor, it may excite an electron out of its energy level and consequently leave a hole. This process is known as electron-hole pair generation. Electron-hole pairs are constantly generated from thermal energy as well, in the absence of any external energy source. Electron-hole pairs are also apt to recombine. Conservation of energy demands that these recombination events, in which an electron loses an amount of energy larger than the band gap, be accompanied by the emission of thermal energy or radiation. In some states, the generation and recombination of electron-hole pairs are in equipoise. The number of electron-hole pairs in the steady state at a given temperature is determined by quantum statistical mechanics. The precise quantum mechanical mechanisms of generation and recombination are governed by conservation of energy and conservation of momentum, as the probability that electrons and holes meet together is proportional to the product of their amounts. The product is in steady state nearly constant at a given temperature, providing that there is no significant electric field or externally driven pair generation. The product is a function of the temperature, as the probability of getting enough thermal energy to produce a pair increases with temperature, being approximately exp, where K is Boltzmann's constant, T is absolute temperature and Eg is band gap. The probability of meeting is increased by carrier traps, impurities or dislocations which can trap an electron or hole and hold it until a pair is completed. Such carrier traps are sometimes purposely added to reduce the time needed to reach the steady state. Doping. The conductivity of semiconductors may easily be modified by introducing impurities into their crystal lattice. The process of adding controlled impurities to a semiconductor is known as doping. The amount of impurity, or dopant, added to an intrinsic semiconductor varies its level of conductivity. Doped semiconductors are referred to as extrinsic. By adding impurity to the pure semiconductors, the electrical conductivity may be varied by factors of thousands or millions. A 1 cc specimen of a metal or semiconductor has of the order of 1022 atoms. In a metal, every atom donates at least one free electron for conduction, thus 1 cc of metal contains on the order of 1022 free electrons, whereas a 1 cc sample of pure germanium at 20 degrees Celsius contains about 4.2 times 1022 atoms, but only 2.5 times 1013 free electrons and 2.5 times 1013 holes. The addition of 0.001% of arsenic donates an extra 1017 free electrons in the same volume, and the electrical conductivity is increased by a factor of 10,000. The materials chosen as suitable dopants depend on the atomic properties of both the dopant and the material to be doped. In general, dopants that produce the desired control changes are classified as either electron acceptors or donors. Semiconductors doped with donor impurities are called N-type, while those doped with acceptor impurities are known as P-type. The N and P type designations indicate which charge carrier acts as the material's majority carrier. The opposite carrier is called the minority carrier, which exists due to thermal excitation at a much lower concentration compared to the majority carrier. For example, the pure semiconductor silicon has 4 valence electrons which bond each silicon atom to its neighbors. In silicon, the most common dopants are group 3 and group 5 elements. Group 3 elements all contain 3 valence electrons, causing them to function as acceptors when used to dope silicon. When an acceptor atom replaces a silicon atom in the crystal, a vacant state is created, which can move around the lattice and functions as a charge carrier. Group 5 elements have 5 valence electrons, which allows them to act as a donor. Substitution of these atoms for silicon creates an extra free electron. Therefore, a silicon crystal doped with boron creates a p-type semiconductor, whereas one doped with phosphorus results in an n-type material. During manufacture, dopants can be diffused into the semiconductor body by contact with gaseous compounds of the desired element, or ion implantation can be used to accurately position the doped regions.